Do you know how much power an F1 engine has, how energy recovery works, and when teams can replace which parts without getting those pesky penalties? No? Well, you're in luck, because we'll be answering all of these questions and more. So let's get started. Formula One is on the cutting edge of energy technology, and its latest power plant is one of the most complex in the sport's history. In fact, today's engines are so complex that they require a pre-start routine involving laptops, remote operations, and a slew of brilliant engineers before they can fire it up. First and foremost, because it's a hybrid, a modern F1 engine is no longer referred to as an engine. Instead, it is referred to as a power unit. It consists of a petrol internal combustion engine and electrical motors powered by an energy recovery system. When they were first introduced in 2014, they were chastised for their lack of noise in comparison to the previous generation's ear-rattling V8 and V10 monsters. But these are some of the most powerful and efficient power units in Grand Prix history. The combined power output of the petrol and electric elements is around 1,000 brake horsepower, which is miles above any normal road car. The petrol engine revs at 15,000 revolutions per minute, which is again significantly higher than that of a road car. This all means an F1 car can cover 0 to 60 miles per hour in about 2.6 seconds and top out at around 230 miles per hour, depending on the amount of wing it's running. The engine is a 4-stroke 1.6-liter turbo V6. It's built to strict dimensions and material constraints, with cylinders arranged at a 90-degree V configuration and 2 inlet and exhaust valves per cylinder. The turbocharger works by using a compressor to pressure charge the engine. It is powered by airflow from the car's exhaust, which is routed through a turbine connected to the outlet system. For those who understand engines, the compression ratio for each cylinder must not exceed 18. The fuel pressure in the injectors must be 500 bar gauge or lower, and the fuel mass flow must not exceed 100 kilograms per hour, scaling down at lower revs. The fuel mass flow is critical because it means that the amount of petrol going into the engine is limited, limiting the revs and power that can be produced, and encouraging teams to design more efficient engines. The cars run on fuel composed of compounds commonly found in commercial fuels, with no power-enhancing chemical compounds. Nowadays, advanced sustainable ethanol must account for at least 10% of the fuel. The cars reportedly consume around 135 liters of fuel during a race, which is a third less than they did with the other thirstier V8s. So now that we've gone over the engine portion of the power unit, let's move on to the engine recovery system. In a nutshell, the ERS recovers energy from the exhaust and brakes and converts it into electricity, which can be used directly by the electric motors or stored in a battery for later use as an extra power boost. The MGU-K, or Motor Generator Unit Kinetic, is an electric motor connected to the crankshaft of the engine. In regenerative mode, it functions as a generator, slowing the vehicle via engine braking and producing electricity to charge the battery. In drive mode, it transforms into a motor, directing electricity to the wheels for increased acceleration. The system is only allowed to generate a certain amount of energy per lap, roughly 33 seconds of maximum power boost, but it can store twice that amount, allowing a team to be strategic and save and use energy at different times. The MGU-H, or Motor Generator Unit Heat, is more complicated and is used in conjunction with the turbo, which itself works by using exhaust gases to spin a turbine that pressurizes the engine. As a generator, the MGU-H provides resistance to the turbo spin, preventing the turbo from producing too much boost at high power, and converts that energy into electricity that is stored in the battery. As a motor, it is used to keep the turbo spinning when the driver is not on the throttle, reducing turbo lag and smoothing the delivery of power, which is more efficient than the alternatives that use fuel. Importantly, the electricity generated by the MGU-H can be used directly to power the MGU-K, adding to the 33-second maximum that can be used from stored energy each lap. That means that the more electricity the team can generate from the MGU-H, the longer they can use the electric power boost. The entire system, including all parts and accessories, must weigh no less than 150 kilograms, with the storage component accounting for 20 to 25 kilograms of the total. The MGU-K has a maximum power output of 120 kilowatts, which equates to about 160 brake horsepower. To prevent electric-powered superstarts, its use at the start of the race is limited until the car reaches 100 kilometers per hour. The MGU-K must weigh no less than 7 kilograms and have a maximum torque of 200 Newton meters at 50,000 RPM. Meanwhile, the MGU-H is 3 kilograms lighter and can spin up to a massive 125,000 RPM. So we know that ERS provides additional power to key car components, but how are these devices used in practice? The MGU-H is always active because it supplements the car's power more passively by keeping the turbo's compressor spinning all the time, whereas the MGU-K supplements the car's power more directly by sending extra power down the crankshaft. As a result, the MGU-K is used in a more active, strategic role. Before the start of each race, teams choose which sections of the circuit they will activate the MGU-K and for how long it will stay active. Drivers are not required to use all of the power in one go. For example, they can use a few seconds of the MGU-K's power on one section of the track and a few seconds more on another. The driver and the onboard computer make the decisions. Teams create engine maps that's set up to deliver electric power in various ways, and drivers simply choose between them and let the car do the rest. Overall, the hybrid system adds another level of strategy to a race, since it can give drivers an advantage over other drivers on certain sections of the track. Another factor to consider when discussing hybrid power is the inherent safety risks that come with it. The ERS is a seriously high-voltage piece of kit. It operates at up to 1,000 volts, so it can give off a very hazardous electric shock. To reduce risk, high-voltage cables are colored orange and have a voltage cutoff when disconnected. Hazard warning signs are installed in the main energy storage enclosure, MGU-H and MGU-K, and all high-voltage junction boxes. The ERS can also be shut down in several different ways, and to show its operating and installation state, it is fitted with status lights on the top of the airbox, glowing green when safe and red when not. In 2019, after retiring from the Bahrain Grand Prix, Daniel Ricciardo was told to jump from the car without touching it after the red light came on, and his Renault team declared it electrically unsafe. Luckily, that doesn't happen often. So far, we've covered the fundamentals on how the power unit's components work together to generate power in today's F1 cars. But if you've been following the season so far, you've no doubt heard a lot about so-called engine penalties. But what exactly does that mean? Years ago, there were no restrictions on engine use, and teams spent millions of dollars developing special qualifying spec engines that were tuned to perfection but only lasted a few laps before revving themselves to submission. Now, to keep the cost down, the number of power units allowed in a season is restricted, with each driver allowed no more than 3 engines, 3 turbochargers, 3 MGU-H, 3 MGU-K, 2 energy stores, 2 control electronics, and 8 sets of engine exhaust systems. Teams are permitted to exceed their assigned number, but will incur grid position penalties if they do so power units are now built to be more robust than in the past. This effectively lowers the cost of participating in F1, while also making it a more environmentally conscious sport with less waste. It also adds another strategic component because teams rarely stay under their allotted amount, with penalties often imposed around midway through the season. The current units will not last forever, as F1 is already planning for the next generation. There is now a freeze on current designs, which means that teams are no longer permitted to develop them. This is to free up time and resources for the development of a new, more industry-relevant hybrid engine to be introduced in 2025. The new regulations will prioritize environmental sustainability, with plans to use fully sustainable fuels and significantly simplify the design to save money. How do you think these changes will affect the Formula One landscape as a whole? Let us know in the comments section down below.